Imagine a world where robots see and react almost instantly, where self-driving cars might spot dangers well before they fully appear.
Uh-huh.
Well, scientists at RMIT University have just unveiled a device that could bring that future closer. It's a new brain-inspired piece of tech. Let's dive in.
Yeah, and what's really striking here, I think, is that it's not just, another small step up in processing power.
Right.
This device, it can actually detect movement, store visual information, and process it all inside itself. No need for a separate computer hooked up.
Exactly. No bulky external systems for those basic but crucial tasks.
It's like a self-contained visual brain almost.
Precisely. And that's what we're digging into today. We've looked closely at the research from RMIT, which was published in Advanced Materials Technologies. We want to unpack how this neuromorphic device actually works and, why it seems to have such exciting potential in different fields. Our goal here is really to pull out the key ideas and explain why this tech could be a major leap.
So let's start with that basic idea then. It's neuromorphic. What does that actually mean? Like, how does it operate differently, and what are the big advantages?
It basically means its design and function are inspired by the human brain. I mean, think about how incredibly fast and efficient our own brains are at processing what we see.
Right.
Professor Sumit Walia, who led the research, he believes this approach could lead to ultra-fast visual processing. But what does that speed really give us?
Well, it's not just about speed, is it? This neuromorphic design, it's also inherently energy efficient.
Ah, okay.
Traditional digital systems, they can chew through a lot of power, especially with complex visual stuff. This device uses what they call analog-style processing.
Analog style, like our brains.
Exactly. Much more energy efficient, mimicking how our brains work on surprisingly little power.
Right. Professor Walia actually said this method can greatly reduce the amount of energy needed to perform complex visual tasks compared with digital technologies used today. So potentially huge energy savings to go along with the speed. And the secret sauce seems to be this one particular material.
Indeed. At the core of it all is molybdenum disulfide. MoS₂ for short.
MoS₂.
And it's incredibly thin material. We're talking a single layer of atoms thick.
Wow, atomically thin. It's hard to grasp that something so small can do so much. And apparently tiny flaws, actual defects at the atomic level, are key to how it works. How does that work?
It sounds counterintuitive, doesn't it?
Oh, well.
But yeah, these tiny imperfections in the MoS₂ structure are actually where the light detection happens.
Yes. Really?
They're the spots that absorb photons, light particles, and turn that light energy straight into electrical signals. Kind of like, specialized cells in our own retinas.
Okay, so the flaws aren't a bug, they're a feature.
Precisely. This direct conversion is a big part of why it's so efficient.
Professor Walia explained it really well. He said the device mimics the human eye's ability to capture light and the brain's ability to process that visual information, enabling it to sense a change in the environment instantly and make memories without the need for using huge amounts of data and energy.
Right. And he contrasted that with current digital systems where, more complex data often means way more power needed.
Yeah, which can really limit how well they make decisions in real time, can't it?
Absolutely. Think about current computer vision.
Yeah.
It usually captures frame after frame of video.
Loads of data.
Exactly. Vast amounts of data that then needs processing. That takes time, takes energy. This new device, it takes a different route.
Which leads us to the experiments they did. They showed it could detect a waving hand moving without needing to capture every single frame. They called it edge detection. Why is just looking at the edges, the changes, so much more efficient?
Well, imagine sketching something. You capture the main outlines, the movement, the shape.
Right.
Without filling in every tiny detail constantly. This focus on just the changes, the edges of movement, drastically cuts down the information that needs processing.
Okay, so less data, faster speed, lower energy.
You got it.
And they'd done some previous work in this area, hadn't they? Using UV light.
They had, yes. They explored neuromorphic computing with ultraviolet light before. But this new work is specifically in the visible spectrum.
The light we actually see with.
The light we see with, exactly. And one of the PhD scholars, Tia Ong, pointed out something crucial.
What was that?
He said the device accurately mimics leaky integrate and fire, or LIF neuron behavior.
LAF. That sounds familiar from neuroscience.
It is. It's a really fundamental way our own neurons process signals, and it's a key building block for creating these artificial spiking neural networks.
So the earlier UV work was more about still images. But this new stuff adds motion detection in visible light. That feels like a big step.
It is a significant step forward. And importantly, the memories the device creates, whether from visible or UV light, they can be reset, wiped clean.
So it can learn and forget, essentially, ready for new input.
Exactly. Ready to go again.
Okay, so we have this fast, energy-sipping, brain-like device. What kind of real-world impact are we talking about? Where could this actually be used?
Well, let's loop back to those initial thoughts about the future. The potential for much, much faster response times in autonomous systems is just huge.
Self-driving cars, for instance.
Definitely.
Yeah.
Imagine a car being able to instantly detect and react to, say, a pedestrian stepping out.
Yeah.
That split-second difference could genuinely be the difference between a close call and, well, something much worse.
Professor Walia really hammered this point home. He said, neuromorphic vision could detect changes in a scene almost instantly without the need to process lots of data, enabling a much faster response that could save lives.
That really puts it starkly, doesn't it? Life-saving potential.
It does.
And Professor Akram Al-Harani mentioned another key area, human-robot interaction.
How we work with robots.
Exactly. If robots can perceive and react to what we're doing with almost no delay, we could see much more natural, seamless collaboration. Think manufacturing lines, maybe personal assistants at home.
Right, robots that can actually anticipate or react smoothly to our movements.
Yes, in factories, maybe even as assistants that feel more intuitive because they react instantly without that processing lag we sometimes see now.
Okay, that paints a compelling picture. But what's next? I mean, is this ready to roll out now?
That's the big question, isn't it? Scaling up. Right now, they've shown this works with basically a single light detector, 1 pixel, effectively.
Yep, just 1 pixel. Okay.
The next major hurdle is scaling that up, creating arrays with thousands, maybe millions of these pixels, more like a digital camera sensor or, our own eyes.
That sounds like a significant engineering challenge.
It is. But they have received funding from the Australian Research Council specifically to help with this scaling effort.
That's a good sign. Shows confidence.
It does. And Professor Walia was also quite clear that the current system is still, in his words, a simplified model of brain processing.
Meaning there's room for improvement, more complexity later.
Absolutely. Lots of room to grow. Future work will likely focus on optimizing these for specific tasks, maybe needing more complex vision processing.
And pushing the energy efficiency even further, I imagine.
That's always a goal, yes.
Yeah.
Plus, they're looking at hybrid systems.
Hybrid, meaning?
Combining the strengths of this analog neuromorphic tech with the precision you get from conventional digital electronics.
The best of both worlds approach.
Seems pragmatic, doesn't it? Walia described their work as complementary to traditional computing. It's not necessarily replacing it entirely, but offering huge advantages for certain tasks.
Especially those needing low power and real-time vision.
Exactly. And looking even further ahead, they're not just sticking with MoS₂, they're exploring other materials too.
Oh, for what purpose?
To potentially extend the sensitivity into other light spectrums, like infrared.
Infrared, what could that enable?
Well, imagine real-time tracking of global greenhouse gas emissions from space, perhaps. Or maybe highly sensitive ways to detect environmental pollutants.
Wow, okay. So from safer cars all the way to global environmental monitoring, the scope is really broad.
It seems to be, yes. The underlying principles are quite powerful.
And for anyone wanting the nitty-gritty details, the paper is Photoactive Monolayer MoS₂ for Spiking Neural Networks Enabled Machine Vision Applications. It's in Advanced Materials Technologies.
Correct. And RMIT has also filed a provisional patent on this, which again signals they believe it has real commercial potential down the line.
So, wrapping up, this feels like a really significant step towards genuinely brain-inspired vision, doesn't it?
I think so. It really demonstrates the potential for autonomous systems that aren't just faster, but also much leaner in terms of energy use.
Which is critical for actually deploying them widely.
Absolutely critical. Yeah. That energy efficiency, combined with these unique properties of MoS₂ at the atomic level, that seems to be the magic combination here.
So it leaves us with a pretty big thought, doesn't it, for you, the listener, to ponder.
What really are the long-term implications if we develop machines that can see and process the world with the speed and efficiency of a brain, or maybe even better?
Yeah, how does that fundamentally change our relationship with technology, our jobs, our daily lives?
What completely new possibilities might open up that we haven't even conceived of yet?